So good morning everyone, welcome to Turbulence. We shall continue the lectures. Last time we finished chapter 4 where we looked at mean flow equations. However, we did not fully finish, we almost finished. I promised to do a problem from the problem set for you. So we'll do that problem and then we go to the next chapter, which is another exciting chapter. So I want to solve exercise number 3 for you. Suppose that in a flow, the mean passive scalar, angle brackets phi, can be expressed as a function of 3 coordinates x, y, and z along the Cartesian system with unit vectors I, j, and k. So be careful, this is a unit vector, I, j, and k, so that the mean passive scalar can be expressed as a function of the coordinates. Right? With x plus y squared minus z cubed. Obviously, there is no physical significance for defining this. I just defined it. This could be 2x, maybe no y, and then minus z. So totally arbitrary. What I want to do is this. Oh, by the way, the phi naught, phi 0 was just some constant. Assuming that the gradient diffusion hypothesis applies to this flow and the passive scalar field, I want to show that the passive scalar flux, remember this was a turbulent flux and small u and phi prime are the fluctuations, the mean of the covariance of the fluctuations is along the flow unit vectors, and at location 1, 1, 1 is equal to this expression. So, you notice the passive scalar flux is not a scalar, it's actually a vector in its own right. So we want to calculate this. Okay. So let's see how that could be done. Example 3. The mean passive scalar is equal to this constant phi naught, phi 0, x plus y squared minus z cubed. And I'm interested at x equal to 1, y equal to 1, and z equal to 1. Using the gradient diffusion hypotheses, the vector of the flux is equal to minus diffusion coefficient times the gradient of the mean passive scalar. This was the very definition of the gradient diffusion hypothesis. So let me remind you, this is the down gradient diffusion hypothesis. Down gradient diffusion hypothesis. The down is because of the negative sign, and the gradient is the gradient. Okay. Now we should calculate this turbulent flux vector. Remember that, be careful. I have put vector u here. What does it mean? It means that I'm actually looking at three fluxes, right? I mean, I could talk about flux in the x direction, flux in the y direction, and flux in the z direction. So actually, I'm showing three equations to you, if you will. Of course, you could do them, tackle them one by one. That's fine. But I just showed all three equations together. What is the gradient? The gradient. Let's write the gradient. If you consult the appendix of the book, you will find this equation for the gradient. A spatial derivative of the quantity of interest with respect to the x component plus the spatial derivative with respect to y component plus the spatial derivative with respect to the z component. There it is. So this is my gradient. Is gradient a vector or is it a scalar? Vector, right? Because I have I, j, k there. I have three components there. If you like something like that, I mean, it's the same concept, but can represent it in a different way. I mean, this is a vector. This is a vector. So what is it for this particular concentration field? What happens if you take the derivative of this expression only with respect to x? 1. But then you have a phi there, right? It should get multiplied. So phi naught I. What about the next component? Do you know what it is? 2 y phi j minus 3 z squared phi k. So I found my gradient. This was my gradient. It's very nice. Now I should evaluate this flux knowing this gradient of the flux. Toward the diffusion coefficient, phi naught, and I can just put I plus 2y j minus 3z squared k. And at the point of interest, x1, y1, z1, I can write this, I can write as a scalar flux, the vector is equal to, at 1, 1, 1 is equal to minus phi, minus gamma t, phi naught, I plus 2j minus 3 k. I just replaced the numerical values for x, y, and z in this expression on top. Can you tell me what does the meaning of a hat on top of an I or j? Unit vector, which means it's a vector, but it's just a unit vector. The magnitude of that vector is 1. Unit vector along this direction unit vector along this direction. Now, I found a vector in space, right? This is a vector. This is a full vector space. If I want to find a unit vector in that direction, there's a way to calculate it. Unit vector along direction. This is how you do it. You take the vector and you divide it by the magnitude. So take that vector, divide it by the magnitude of that vector. In other words, if you divide any vector by its magnitude, you get a unit vector. Right? Seems to be obvious. So on top, I had the vector minus gamma t phi naught I plus 2j minus 3. Okay. The bottom, and I only have a magnitude. What is the magnitude of this vector? And you can make a guess. What is the magnitude of this vector?
Root 40.
Excellent. Very good. You are gifted. Okay. You just take each component and raise it to the power 2. Okay. Well, it's very convenient because the constants that I had would cancel from top and bottom, and what I get is at the very end is this. Minus 1 square root of 14 I plus 2 plus 2 square. Oh, sorry. I had a minus sign up here. Minus 2 square root of 14 and plus 3 square root of 14. If you like, I can even annotate to you. I promise to do as much annotation as possible. If you like, this is the x component of the flux. This is the y component of the flux. Velocity in the y direction is v. And this is the z component of the flux. Velocity in the z direction was w. Does it make sense? So you're looking at components of the flux, and all of them together are supposed to show you the components. However, I have to be careful. I still have the magnitude of the whole thing divided. So it's more accurate to write this as the following. We should still put this at the bottom. Denominator. The same common denominator for all of them. So let me put sort of the description of this in words. This is the unit vector specifying direction of turbulent acid scalar flux. It's a very powerful concept. That means, well, you just follow the mathematics. You can pretty much calculate anything in the three-dimensional world, and the motion and flux of any quantity of interest in the 3D space. It's very powerful. Any questions with that? So now I would like to switch gears and start the next chapter, which is just as exciting. The next chapter is called wall flows. So what people do in the study of turbulent flows, you always simplify the flow for a given application, so you can deal with it conveniently and with minimum amount of effort in mathematics and computational power and modeling. So you always start with the general equations and simplify them down to what you can solve or analyze. Wall flows is an example of those types of flows, and in the more broad sense, flows can be understood as internal flows and external flows. I mean, if you want to divide flows in one way, it's to look at internal flows and external flows. Internal flows are flows in pipes and buildings that are fully surrounded by surfaces. For example, the air in this room. The air in this room is circulating in some way. Well, it's bounded by a lot of walls and ceilings, it's fully enclosed. But the flow on the roof is only bounded by the roof surface. It's open to the atmosphere. So that's an example of an external flow. Okay? So internal flows and external flows. External flows are partially surrounded by surfaces, as the definition. Now, we are not going to subdivide wall flows for internal flows and wall flows for external flows. We just want to talk about wall flows in general. We only care about the very surface adjacent to the flow. That one surface. So we do not restrict our discussion to internal or external flows. Just underline that. So transport equations and the balance of mean forces, we do not restrict our discussion to internal or external flows. Well, we'll discuss fully developed flows near walls, defined as a state where velocity statistics no longer vary in the direction of the flow. So anytime you study flow near a surface, well, the flow is going parallel to the surface. I mean, there's no way that flow can go into the wall, right? It has to go parallel to the surface. And if this flow is fully developed, the statistics no longer change in the direction of the flow. That means if you calculate mean velocity, it's going to be the same here, it's going to be the same here, it's going to be the same there. If you calculate variance of u component of velocity, it's going to be the same here, it's going to be the same here, it's going to be the same here. Wind close to the Earth's surface can be approximated as a fully developed flow if the terrain is homogeneous in its very long field. Now, suppose that the influence of the wall on the flow is diminished at a distance of delta away from the wall in the normal direction, where the free stream velocity is almost achieved completely. For example, let's say almost 100%, 99%. This distance we know as the thickness of the boundary layer. That is a thin layer of viscous fluid close to the solid surface or wall in contact with a moving stream. Okay, so in which the velocity varies from 0 at the wall up to some maximum value. So usually 99% of the free stream velocity. And delta itself is known. As bound layer thickness. So here I'm referring to figure 5.1. So let me show it to you in a figure. Well, this is the wall surface. The flow is in the x direction. The direction normal to the wall is y, and associated velocity is v. The direction sort of sideways in the span-wise direction was z or w. So the flow is along the x direction. The wall surface is actually the zx plane. So the flow near the surface would approach zero. This is so-called the no-slip condition. The wall imposes a friction on the flow. At the very contact point, the flow is not moving. And then it gradually reaches up to a free stream value of u naught or u0. That's the velocity far away from the wall. Somewhere in the transition, the flow reaches almost u naught, let's say 99%. In that location, we define the depth of the boundary layer, or the thickness of the boundary layer, and we show it by Greek symbol delta, small delta. And so that's what that paragraph was talking about. You can calculate some sort of bulk velocity of the flow within the boundary layer. Of course it varies, but if you calculate the average of that velocity in the entire boundary layer thickness, it's designated by u bar. So this is the bulk velocity of the flow within the boundary layer. So just integrate mean flow from distance 0 from the wall all the way to the top of the boundary layer thickness, and then divide by boundary layer thickness. If you think of it, this is a simple formula for an average, but it's the average for a continuous variable, maybe just an average. So we know this as u bar, or bulk velocity. And of course, this velocity must be less than u naught. Must be less than u naught. It's not hard to be convinced of that, because if you take the average of all of these velocities, the average velocity is somewhere probably like here, right? So u naught is the average of all of these velocities, somewhere in between. It's greater than 0, less than u equal. Now, before I develop the transport equation, Navier-Stokes equation for wall flows, I want to show, to draw a picture, a schematic, which is important, because it helps me develop the equation for you. I want to discuss the concept of developing versus fully developed flow. Developing versus fully developed flow. We talk about it in the definition, but what does it mean? What does developing and fully developed flow mean? Let's say there is some flow coming. This flow going from left to right in the open space. And the free stream velocity is u naught. Certainly this is a sort of a mean velocity, even though I don't put the angle brackets, but I infer it's a mean velocity. Now what you do, you put a plate. You put a plate in front of this flow. If you like, now I have put a surface or a wall in front of the flow. So this is a plate. What happens is that the flow is going to interact with the plate. It's going to come to stop here, and gradually a boundary layer develops, or a boundary layer, so the thickness develops. I choose the x direction to be along the flow, consistent with the diagram I put up. Well, obviously the flow is going to slow down in this thickness layer because the plate imposes a friction on the flow. But far away, I still have the undisturbed flow, mean flow, very far away from the plate. And I can look at mean velocity in that layer. I want to know what it is. What is the mean velocity in that layer? I could be thinking about anywhere. It could be top of it, bottom of it, here, 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 here. It's very interesting to know what mean velocity is in the x direction. And certainly this mean velocity must be less than the free stream velocity because the plate slows down the flow. I know that it must be less than u0, but I don't know what it should be. If you notice here, the boundary layer thickness is not the same. It actually starts growing, but at some point it reaches a fixed level. While this is developing to reach the fixed height, I call this flow I call this the developing flow, which means it hasn't fully developed yet, but it's just developing. So developing flow. Flow, which means that horizontal variations in the flow properties exists. I mean, I have horizontal variations in flow properties. In flow properties, which means that if mean velocity in the x direction u was some number here, that's going to change along the horizontal direction. As I move forward, the mean velocity is changing. However, after I develop into a fully developed flow, fully developed flow, no horizontal variations in flow properties exist. There is one exception, except for absolute pressure. Which means that if I looked at mean velocity in the x component u, it would be the same as I move down the stream of the flow in the horizontal direction. So that would be the same. V would be the same, W would be the same, the variance of u would be the same, the variance of W would be the same. The Reynolds stress UV will be the same, UW, all of those will be the same, except for absolute pressure. And you will see in the equation why that is so. I mean, obviously here we made a simplification. In this this boundary layer might grow indefinitely. I mean, actually it slows down, but it just keeps growing. I'm just ignoring the very gradual growth of the boundary layer. So I'm just neglecting the gradual growth, right? I'm neglecting the gradual growth. I'm saying for all practical purposes, I can assume it's this fixed height after some point, approximate as fully developed flow. Or in other words, I approximate, not definitively say it's fully developed, as fully, approximate as fully developed flow. write it down into the equations. First, I will continue with the continuity equation, show you how that equation is satisfied in all flows. Then I will develop the momentum equation for it. So here is what I'm going to say. I'm telling you that, okay, by definition, the mean velocity component u does not vary as a function of x for the fully developed flow. Okay? And that the mean velocity in the vertical direction, or sorry, in the span-wise or sideways direction is 0. Okay, so how do I support this claim? Well, I have a very symmetric sort of flow, and flow is going along the x direction in the boundary layer near the surface. If this is a fully symmetric sort of flow infinite field, there is no reason why the flow should steer to the right. There's no reason why the flow should steer to the left. For the perfectly symmetric and homogeneous condition, the flow will just go along. It's not going to steer to the left or right. So I just supported this claim, right? There's no mean motion sideways. It just goes forward. Now, I make another claim. I make the claim that the vertical gradient of the vertical mean flow should be 0. How do I support this claim? Well, I can support this by the continuity equation in the following way. Continuity equation. I write the continuity equation. I got the continuity equation. Can you help me fill in the missing parts here? For a constant property flow, what am I taking the partial derivative of?
Velocity.
Mean velocities, yeah. U, V, W. Okay. I just convinced you that mean velocity in the z direction is 0. W is 0. If W is 0 everywhere, so should be its spatial derivative. I always told you mean velocity in the x direction does not vary as a function of x. Right? What do I have here? I have variation of u as a function of x. I told you it does not vary by definition. So what should this term be? Also 0. Then I only have one term left, which this by the continuity equation, it must be itself equal to 0 also, right here. Remember, continuity equation, well, I didn't write it for all flows. I just wrote it for constant property flows. For constant property flows. Be very careful. For incompressible flows, this does not satisfy. Okay, so we found an important result here. So let's move forward. The next thing I want to do is I just want to derive the boundary equation for the u component of the momentum. And I'll do it separately on another piece of paper. Let's take my time slowly, show you how this is being done. So mean momentum equation in the y direction. So let's do it. So mean momentum. In other words, I want to deal with mean x, in fact, momentum in y direction, or if you like, direction normal to the wall. Direction normal to the wall, or wall normal. I'm going to start with the Navier-Stokes equation. So I start with the total derivative. And I could write this for any component of the momentum. Let's say I was writing it for uj. Total derivative of the mean momentum, j direction, is kinematic viscosity Laplacian of mean momentum in the j direction minus the Reynolds stress ui uj partial xi, so have that one, minus the modified pressure term. So let me label these. This was total derivative. I promised I'll do it as much as I can. Total derivative. What was this term called? Surface forces. These are the forces that act on the surface of the control volume. Left, right, top, bottom, front, back. What was this called?
Reynolds stress.
Yes, Reynolds stress forces. Which also act on the surfaces of the control volume. And then what was this one called?
What is that?
Well, pressure and body forces. Pressure and body forces. Well, pressure applies to just the surface of the control volume, but body forces apply everywhere, right? Like gravity, it would apply on everywhere. But anyway, we group all of them into one term. Let me just remind you what the total derivative was. The total derivative, the mean quantity would be, by definition, the partial of whatever I'm interested in with respect to time plus the mean velocity vector dot product with gradient of whatever I'm interested. I mean, I could put u component, v component, w component of momentum, right? I could put temperature here. I could put passive scalar here. Could be anything there. For let's say I had uj, I was looking at the second component. Essentially, I was looking at the momentum in the y direction, v. I was looking at v. This would be the second component. of momentum on the total derivative side, I mean on the left-hand side, according to this top definition, I would have partial v partial t. That's the time derivative that I need there. Now we have the dot product. So I need u times the component of the gradient with respect to the first coordinate direction. That would be partial v partial x. Then I would have v times second component of the gradient. So I'm done with the left-hand side. This is the total derivative of v. On the right-hand side of the momentum equation, I have kinetic viscosity Laplacian of v minus Reynolds stress. So here, I'm going to have u v minus v squared partial y minus 1 over rho partial p partial y. Okay, now this is the full momentum equation for the v component. A few things will be assumed. For example, there's no time variation of the v component of momentum. In other words, the boundary layer flow, the wall flow is a steady state. As time changes, v component of the momentum is not going to change. In fact, we assume for this simple system, none of the components of momentum change with time. I also found that partial v partial y was also 0. I just showed it to you in the last page. That came from the continuity requirement. Just came from the last page. Also, I told you already anyways that components of none of the statistics will change in the fully developed flow in the direction of the flow. And x is the direction of the flow. So there's no change in mean vertical velocity there either. So all of the left-hand side is 0. I mean, it sounds like a very easy course. Like most terms end up being 0. So it's nice. It's 0 equal to 0 and end of story. Well, not quite so. Now, the Laplacian would also be 0 because Laplacian involves derivatives. And all derivatives of v will be 0. Either derivative with respect to x will be 0 or y will be 0. So that derivative would be 0. And again, this term shows variation with respect to x or flow along or direction along the flow. For fully developed flow, none of the statistics change with the flow direction. And this is a statistic, uv. This is a statistic. Is some quantity. It's not going to vary for a fully developed flow. I'm only left with the last two terms there. Okay. Which is this. I mean, I could sort of knock out the negative sign, so here I'm left with this. Partial of variance of v, partial y, plus 1 over rho or density, partial pressure, partial y. Sounds like this is just a differential equation in the y direction. It's a very ordinary differential equation. So I can integrate this over, y. I just integrate this in the y direction. This is what happens. I integrate the left-hand side. The left-hand side integration would be 0 dy, and I vary y from some initial value 0. I start from the bottom of the boundary layer at the surface. The y, or distance to the surface, would be 0. I integrate from 0 to some given height. I'm not saying I'm going all the way to the top of the boundary layer, anywhere in between. If you notice, I put y star. Why did I put y star here? It is just good and careful notation in mathematics, right? I mean, here y is the variable of integration. Y star is not, here is not the variable of integration, it's just the limit of the integration. So I have to distinguish between this y and that y, so I put a star. It's just careful mathematics. A lot of times people are careless, don't do this. I may even fall to the same pitfall and forget it, but really, let's be meticulous. Here, the first term would be that, and the next term would be that. Now it looks like the only variation, it's variation normal to the wall. In other words, there was no variation in the z direction either because of homogeneity and symmetry. And a lot of the components did not vary in the x direction along the flow. So really the only meaningful variation for most of these variables is y. So I can replace partials with differentials. Or D. Like the partial symbols I replace with differential symbols. I mean, this would be dv squared dy or dp dy. And it simplifies extremely if you did that. One, you just watch what happens. On the left-hand side, integral of 0 is some constant. So I have some constant. What happens to this other integral? Well, the integral of a derivative of something is that something. You think about it, the integral and derivative cancel each other. So I get v squared at some given location y, right? You integrate it from 0 to some height of the boundary layer. Okay? And then, same thing with p, the integral of the derivative of p is p itself. At some height. Now, what about c? What about constant c? Let's see if we can deal with that. At y equal to 0, if you integrate it very close to the wall, at y equal to 0, then there is not going to be any fluctuations close to the wall. Do you agree? The flow is almost stopped at the wall. So there's no flow at the wall, stagnant, nothing is moving, so there can't be any fluctuations either. So variance of V must be 0 there. Therefore, this constant will only be related to pressure at the wall. We also know pressure at the wall. We could use symbol W to make sure we mean pressure at the wall, P sub W. Pressure near wall. So you remember pressure, this is pressure near wall. And therefore, now that I know what that constant is, then V squared variance of V plus pressure over rho must be equal to pressure at the wall over rho. I mean, note that I dropped the subscript y here because I could mean at any height. This could be anywhere from surface all the way to the top of the boundary layer. And at any height, the sum of these two terms is equal to the pressure at the wall, right? Divided by density. Why did I put pressure as a function of x? I should remind you, because when I defined, I told you for fully developed flow, nothing will change horizontally in the direction of the flow except for absolute pressure. I made one exception, and you will see the need for that exception in a bit. So this wall pressure is a function of horizontal location, so it is a function of x. I mean, you could notice a lot happened here, right? I mean, this is just a page of simple derivations, but a lot of deep thinking there, which is very important. And I really did just do all the work to come back to the chapter and show you that when I write this down, you know where this is coming from. Again, speaking of labeling terms, this is a component of the Reynolds stress, agreed, because variance of V was a component of Reynolds stress. So this is still a Reynolds stress term, and this is still normal unbody forces. So that will do justice to labeling terms. And I just showed you the next equation. Just the next equation, we just derived it for you. Again, and this would be for any height. For any height or y. For any height y. And now I'm going to do something new. I can take the derivative of this equation with respect to x now. Well, first of all, what's the derivative of pressure with respect to x? Well, we could do it for pressure. We'll find that the partial derivative of the mean pressure at any height is equal to the derivative of the pressure at the wall. So why am I making this statement? Well, if you take the derivative of this equation with respect to x, well, the variance should not vary with x. That drops out to 0. Then only two terms remain, pressure anywhere and pressure at the wall, right? And surprisingly, the derivatives are the same. Which means that mean pressure at any height is equal to the derivative of the pressure, the derivative of the mean pressure at any height is equal to the derivative of the pressure at the wall. Which means that if you look at pressure drop in this wall flow, I mean, if this flow is going over a wall, even though this is the x direction, this is y. Even though flow is stopping down and the mean flow changes normal away from the wall, the amount of drop in the pressure is the same at any height. Let's say if you look at pressure drop from here, 0.1 to 0.2 delta P. Pressure dropped from 0.1 to 0.2. If you look at any other height, you get the same pressure drop. Doesn't matter wherever you measure pressure drop in the boundary layer, it's the same. Drop in pressure is the same. The same meaning here, right? If you get rid of the x, change in pressure anywhere is change in pressure at the wall. That's just putting a picture to that equation. It's a very profound result. We can now write the momentum equation in the x direction. Well, I did it for the y direction when I derived it, but you can again derive it for the x direction. You could sort of practice at home maybe. Start with the transport equation and simplify it down all the way to here. You can do that. If you did that, well, the Reynolds stress term and the normal body force will still remain. This time the Reynolds stress would be uv. It's not v squared anymore. But there is one extra term that's left from the surface forces. In fact, this term is coming from the Laplacian. Kinematic viscosity, it comes from there because u shows variation with respect to height. I mean, I'm just showing you. U is changing with height, right? So there is a gradient of u with respect to height. So the term for surface forces will be there. So it's a little bit longer. Now, if we group the first two terms on the right-hand side, I can group these two terms. And I can call these two terms grouped together, I can call them partial tau with partial y. The question is, what is tau then? Okay? Has a very important and significant meaning in turbulent and all of flows. This tau is known as total shear stress accounting for surface forces and the Reynolds stress, but not normal forces. Okay? And as I said, tau can be defined as the sum of rho nu gradient of u with respect to normal direction of the wall minus rho this component of the Reynolds stress tensor. So I need to define it in that way, so now I have derivatives of this with respect to y. So if you take the derivative of this with respect to y, there you get your second order derivative of u, which was here, and then you get the derivative of the Reynolds stress with respect to y, which was here. So if you take derivative of tau with respect to y, you get these terms, and we know tau as shear stress. Can you tell me if tau is a vector or is it a tensor? It's a tensor. So tau is also known as shear stress tensor. Now, I told you shear stress. This equation tells you more things about the physics. Shear stress, well, remember shear would act on the fluid parcel sideways. Somehow you can think of it as friction, sideways friction on the fluid parcel. I'm telling you that this shear stress is balanced by pressure drop. In other words, flow is going along the wall, the pressure is pushing it forward. If there was no pressure, the flow would not go forward. But then the friction is slowing it down, and the two effects cancel each other out. So at the end, you get steady flow. So pressure is pushing, shear stress is slowing down. So at the end, the two cancel each other out. And if you want, I can write this. So this means pressure and friction forces cancel each other. So pressure and friction forces cancel each other. the axial normal stress gradient, so the axial was under the direction of the flow. Normal stress, well, pressure was sort of a normal stress. The gradient of the pressure in the x direction is balanced by the cross-stream shear stress. That's another manifestation of what I just told you. The value of the total shear stress can also be calculated at the wall. Calculated at the wall. So if you put the subscript W here, this means at wall. Has a very important physical meaning. It determines the amount of friction on the flow by the surface, because the surface, the wall, slows down the flow. So this tau tells you something about it. And now I want to put another exciting diagram up for you. Put a picture to this. Total shear stress I defined as tau equal to rho nu gradient of u component of momentum in the y direction, normal to the wall direction, minus density component of the Reynolds stress known as uv. Basically fluctuations along the flow and fluctuations normal to the flow or normal to the wall. What was new? Notice that in the viscosity. And this is telling me something about the components of the shear stress. It means that if you have friction or shear stress in turbulent flow, it's coming from two contributions. The first contribution comes from the viscous or laminar aspect, the viscous side of the flow. The flows have viscosity. Viscosity is some form of friction. It will slow down the flow. That's the first term. And the second term is the turbulent. Okay? So if you like, you can think of this as this term is viscous. Viscous stress. You can think of this term as turbulent stress. And the total stress is the combined effect of viscous and turbulent parts. And I can put a very nice picture to it. Okay, let's say this was the wall, and this was direction y. So this is the wall. I want to see how total stress varies. So this axis is tau, or total shear stress. I want to know how it varies as I move away from the wall. If you look at the viscous part, the gradient of mean velocity is gradually lost, which means very far away from the wall there won't be any gradient, there won't be any viscous action on slowing down. And that's given by the profile of the mean velocity, right? First the gradient is very sharp, and then it sort of approaches u naught, or the free stream velocity. So somehow I know that the first term eventually disappears. Well, I started at wall, T wall. Now, it's pretty interesting. So this term eventually disappears away from the wall. What about the turbulent part? Is the turbulent part significant at the wall? Just look at the Reynolds stress component. Can this term be significant at the wall? Fluid is not moving at the wall, it's just there's no motion, there's no fluctuations as a result. This can be significant. In fact, it would be exactly zero, because nothing is fluctuating there. But the more you move away, these fluctuations come. So I get an opposite sort of a behavior. And then it sort of reaches some sort of plateau. So this is the other term. Okay? If you add these two up, you get the total. You get the total. It's very interesting. Each of them vary quite significantly, but when you add them up, it varies, the total varies very gradually, and it slowly declines. Basically, gradual decrease. So then here you have a gradual decrease. Which means if you're really, really far away from the wall, then there is no shear by the wall. So it just goes to zero, really, really far away. It's a very profound result, and I'm going to put some words here. So this was total. Total shear stress drops gradually with distance. With distance away from wall, or Y. This one was viscous shear. Viscous shear drops sharply with distance away from the wall, and then this was turbulent shear. What should I write? Rises sharply. Okay, so rises sharply. But plateaus. It doesn't go on indefinitely, but plateaus. And I can tell you this is a big deal. If you design any engineering system, like a water treatment plant, combustion engine, ventilation systems, airfoil for aviation industry, if you make anything, it's going to have some walls, and you should know how flow goes around the walls. Even when you design buildings, all the cool aerodynamic buildings, for example, right? Which like high rises, which are safe from wind-induced vibrations. I mean, somebody thought about how the flow interacted with the skin or the wall or the surface of the building. So whatever you do, wall flows are extremely important in fluid analysis and design. This is a big deal. Okay, really exciting. And people have sort of refined the formulation of these the wall flows in a way that you can, if you want, normalize the shear stress at the wall and come with some sort of a skin friction coefficient. Skin friction coefficient. And this type of friction is analogous to the coefficient of drag in bluff body flow. Is to think of any aerodynamic object, like a submarine, a ship, an aircraft. They have a skin friction coefficient, how much friction the skin imposes on the flow. Or your favorite aerodynamic car, sports car, has a skin friction, which you definitely want to know and minimize. Right? So if it's a good aerodynamic or hydrodynamic system, it must have a small skin friction. It's some sort of a drag. So if you divide shear stress at the wall by 1/2 of density free stream velocity, this is one way to normalize the friction coefficient. Alternatively, you can divide by 1/2 of density times the bulk velocity in the boundary layer. I also told you what U bar was. It's just some other way to formulate this. We'll continue. We can't finish this chapter today, but we can maybe say a few more concepts. Any questions so far? Good. The shear stress near wall. Okay, we're gonna go work a little bit more and try to define a couple of things. The total shear stress at any distance away from the wall, it is a function of distance away from the wall. If you remember, it declines gradually. It's a function of distance, y. Is the sum of the viscous stress and the Reynolds stress. And if we know that at the wall, mean velocity is 0, there cannot be any turbulent fluctuations. I just said that. And consequently, no Reynolds stress. So in other words, if you want, at the wall, there's no term left for the turbulent stress. So all of the shear stress is coming from viscous stress. So the turbulent part dropped. People have defined some new scales from the quantities we have had so far. We can define viscous scales that are appropriate velocity scales and length scales associated with the near wall region. The first one is friction velocity and the viscous length scale. Okay, so remember, we understand fluid motion using scales. What is a Reynolds number, right? It's all the gain scales. What's large, what's big, and then how is the flow behaving? Is velocity high, is velocity low, what's happening? Is length large, is length small, what's happening? Is viscosity high, viscosity low, what's happening, right? Fluid analysis is all about understanding scales. Now I want to understand some scales at the wall. Okay? Friction velocity is one of the scales at the wall, and viscous scales is another scale near the wall. And I can define them in this way. If I divide friction stress, total stress, shear stress by density, take the square root, I get this scale, friction velocity. If I do the opposite, divide density by shear stress, but multiply by kinematic viscosity, I get a new thing called the viscous length scale. And if you like, you can actually define a friction Reynolds number at the wall. So this Reynolds number determines the physics of friction at the wall. The relevant velocity scale at the wall is the velocity scale I defined here, friction velocity. The length of relevance was viscous length scale, and nu was kinematic viscosity. And well, just by definition, the Reynolds number, the friction Reynolds number, is just dividing boundary layer height by viscous length scale. So sorry, this was the boundary layer height, delta. So if you divide the boundary layer height by the viscous length scale, you get the shear, the friction Reynolds number. Okay. Just some more definitions, and just some of these other scales pop up, and we will use them. This is one way to normalize the analysis of wall flows. Remember, I mean, anybody who does design pipes has used the Moody chart. Example. What is a Moody chart? It's just some sort of a normalized table to analyze pipe flows and size pipes and pick roughness factors. And, you know, as an engineer, you need to normalize and then solve problems. The standard way to deal with it. We do this the same thing, this sort of normalization with wall flows. And the next normalization quantity is called Y plus, and I'm going to define it here for you. An important parameter in the study of turbulence near walls is the distance from the wall measured in viscous lengths of wall units. So what does it mean? If the viscous length, let's say the length that this viscous stress is very active, is some number. Let's say in this flow over this surface, the relevant viscous scale is 2 millimeters. It could be 5, it could be less. If I divide any height of interest to that viscous length, this gives me a measure of how far away I am from the viscous action. See what I'm saying? It tells me how far away I am into the turbulent region, in other words. So this is a normalized height, that's all. So you divide height, real height, by viscous length scale. And this is a big deal. And so when you normalize the wall flow problem, you say, okay, Manic, my Y plus is 16, for example. He immediately knows that I'm 16 times away from the length scale of viscous action, right? He doesn't need to know what each individual height was or what the specific problem was, but in a normalized sense, the statement helped him understand how far away I was into the turbulent region. See what I'm saying? That's how useful normalization is. Now, I would like to stop here and finish this chapter next time. But any questions? Great. Thanks for coming and joining. We'll resume next time. Do attend the computer assignments because they help you settle the material. Please attend them. Thank you.